Stargate is the world's largest metal 3D printer, entirely built and designed in-house. The core of it includes 3 robot arms, one of which is doing printing and the other 2 are doing post-processing. This is a 6-degree of freedom industrial robot arm, so it can move anywhere within about a 14-foot radius of its center. Right now, the biggest parts we can make are 9-foot diameter and about 15 feet tall, and our printers are only getting bigger over time. We aim to go from print to launchpad in less than 60 days.
We're in an exciting time for spaceflight innovation. There's SpaceX's reusable rockets, trips to the far side of the moon, NASA's Commercial Crew Program is finally getting underway, and there's a startup in LA's aerospace hub that's on a mission to completely 3D print a rocket. We met up with one of their co-founders for a look inside their operations.
My name is Jordan Noon. I'm co-founder and chief technology officer at Relativity. Me and Tim actually met when we were students. We've known each other almost 10 years now. He graduated, went to Blue Origin. I graduated, went to SpaceX. Both Tim and I saw the promise of 3D printing, and we wanted to see the advantage of that applied to an entire rocket.
But this isn't the desktop 3D printing you're used to seeing us cover here at Seeker. This is a different type of additive manufacturing, where an entire assembly line can be built around machines that use powerful lasers to create industrial parts.
There's 2 main advantages that we see by introducing the printing process to rocketry. The first one is reducing the part count on the rockets. So traditionally, rockets can have up to 100,000 parts on them, and we want to reduce that to about 1,000. The second area is in flexible manufacturing. When you have a traditional manufacturing, you end up with a factory full of very expensive tooling. By introducing 3D printing as a baseline to the manufacturing process, you now have a flexible tool rather than a fixed tool. And that makes it much easier to change and modify our designs, especially compared to anyone else in the industry.
While 3D printing has been explored by others in aerospace for years now, Relativity tells us they're doing something different.
Often other companies will take a traditionally manufactured assembly and look at each piece of it and try to figure out which one is best applicable to printing and then print that traditionally designed part.
For Relativity, it all starts from the ground up.
Stargate starts when a part is still on a computer. It's in a digital environment called CAD, or computer-aided design.
Most of the rocket is basically just a system to carry fuel and dispense fuel. And so for that, to make sure you have like the lightest system possible, you want to make sure that wherever you move your fluids inside your rocket, which are liquid oxygen or your fuel, you want to do so super efficiently. Fluid flow can be harder to predict. So that's when we use tools like CFD, which is computational fluid dynamics. And that's basically asking the computer to kind of predict the way that a flow of a certain fluid will move through a manifold and distribute itself evenly. By doing that in the computer, we're able to iterate really quickly. So we can say, hey, how does my flow behave if I have a 1-inch hole? And it'll tell you, and then you move that by like maybe half an inch, and you try different things. From that geometry, you're able to basically tell the printer what it is you want it to make. Just being able to maybe print 3 different designs using the exact same tooling, exact same printer, allows you to just kind of bake that into the process, that kind of trial and error.
And to make these future parts, Relativity leans in on some key printing techniques.
Stargate uses a direct energy deposition method where you're actually feeding a wire into a melt pool and moving that process around. Stargate prints the majority of the structural components on the rocket, and that includes not only the propellant tanks, but the structural attachments, the payload encapsulation fairing, and all of the pieces that aren't the engines on the rocket.
One of the things that makes our tanks special is our ability to kind of 3D print them, and we're able to 3D print them in one piece, which gives us kind of like good confidence in our ability to be completely leak-proof. When we talk about tank, we actually mean like a tank that can hold both liquid oxygen and liquid methane. And so that's usually generally something you either put 2 tanks with or have some kind of complex divider you insert to separate the 2 propellants. That is one of the great advantages for us, is that we're able to print both of those tanks as one part.
On the smaller scale that we use for the engines and other smaller components, we use a methodology called DMLS, or direct metal laser sintering, and that has become pretty commonplace across the industry, and that is done within a bed of powder. That bed of powder is laid flat, and then a laser locally melts material where you want to build up your finished part.
This process repeats itself powder and laser until the part is finished, which could be as many as 10,000 layers.
Here's a version of one of our printed domes. These domes represent the end caps that'll be on the ends of the propellant tanks on our rocket. There's a variety of other equipment out on the shop floor here, including Stargate in the back. We have CNC mills, heat treat furnaces, and a variety of equipment that supports the manufacturing, not only for the rocket, but for making the 3D printers as well.
And another key element of Relativity's production model is automation.
We have a patent that covers the real-time controls during the printing process, and that patent covers novel techniques for applying machine learning and AI. The control station is here on my left, but it's mostly for monitoring now. So you can manually move the arms, but traditionally these are moved in an entire automated manner where you're feeding the part design essentially to it piece by piece, so it knows which parts of it to add at once. Once you know how you want the robot to move during the printing process, you have to be ready to do all of the dynamic controls and feedback. We collect enough data both on what we're putting into the printers and what's coming out of them in order to correlate that and come up with control loops that can maintain the very high quality prints in a way that we could not predict just on our own.
This killer combo of automation, machine learning, and 3D printing promises to deliver a new path for spaceflight.
Our printing technology has surpassed even where sci-fi has put some parts of technology, which is often surprising to see. Aeon-1 is a fully 3D printed rocket engine fueled by liquid oxygen and liquid methane. It is entirely printed in only 3 parts, and that is a testament to the part reduction that is achievable through the printing process. A similar engine with a similar internal configuration could take up to 3,000 parts when traditionally manufactured, and we can make them not only in 3 parts, but print those parts in only 9 days.
There's still plenty of work ahead before these engines are ready for their first official launch, but NASA is paying close attention. They've recently inked a 20-year partnership with the Stennis Space Center for future testing.
We've had over 100 hot fires of that under a variety of revisions, constantly modifying and improving the performance of it as we've gone through that test campaign. The rocket that we're selling is 7 foot diameter and 105 feet tall. It weighs about 120,000 pounds at takeoff, and by weight, it's 95% printed.
This rocket is catching contracts with satellite companies even before it's ever had its first test. They're working towards a 2020 orbital test, with 2021 as their official launch for commercial flights.
We see a future where not only do we have 3D printing, but we also have an automated production line handling everything that comes out of the printers.
3D printing is the special sauce of Relativity, but I think that comes into play in more ways than people realize. You have the ability to basically change your designs and explore the design space at a much faster rate. You need kind of a lot of creativity and a bit of audacity too to kind of look at these problems that have been solved and try to approach them in a different way. And so every day you get to kind of sit down and say, oh, you know, like, have we tried this? Have we looked at that? You really have kind of a blank slate to work with. So it's a lot of fun.
For more science documentaries, check out this one right here. Don't forget to subscribe and keep coming back to Seeker for more videos.